In this interview, I speak with Andreas Bihlmaier, who is the head of Robotics Software Architecture at Intrinsic AI. At the time that this interview was recorded, Andreas was still working at ABB as the chief software architect, and he was a few weeks from making it public that he was going to be moving to Intrinsic AI. As fate would have it, both Andreas and I are now working at Intrinsic AI. I came into Intrinsic through Open Robotics when Open Robotics was acquired by Intrinsic at the end of 2022. With all that being said, I thoroughly enjoyed this conversation. Andreas has a broad and deep knowledge of robotics, and I loved hearing his perspective on a wide range of topics from serverless robotics to Tesla bot and reinforcement learning. We also talked about how to design robots to make future changes easier and strategies to test robots for production. I'm Audro Nash. This is the Sense Think Act podcast. Thank you to our founding sponsor, Open Robotics. Also, thank you to Sergey Karol for suggesting this interview on Twitter. And now, here's my conversation with Andreas Bihlmaier. Hi, Andy. Would you introduce yourself?
Hi, Audro. Thanks for having me today. Yeah, sure. My name is Andreas Bihlmaier, and at time of the recording, I'm Chief Software Architect at ABB. Depending on when you hear this, that might have changed already, but for now, that's where I am.
And what are you going to next?
So I do not yet want to mention what's the next company before it's announced in 2 weeks that I'll be joining there. But I'll definitely stay in robotics and more particular keep focusing on robot software.
Mm-hmm. Now, I'd like to go back quite a bit and just tell me your path in robotics.
Oh, that goes back quite a while. So I actually, when I started my undergraduate studies, I thought I'd go for cryptography, computer security, and operating systems because I had been part of the OpenBSD operating system development as a high school student, and I thought, okay, yeah, that's really interesting in computer science. And then one day I walked into the basement of one of our university labs and saw a swarm of robots there, like, 30, 40 small robots running around sorting Lego blocks based on some projected pattern from the ceiling and communicating with each other, running swarm algorithms. And yeah, that one really drew me into robotics because it was like this experience realizing that code can also reach out into the real world through robots, and this connection between software on the one hand, which I have had already been familiar with, but also with interacting with the real world through highly flexible machines, perhaps even a whole swarm of them, that I found so interesting that I basically took a sharp right turn and changed my major subject within computer science to robotics and a few related fields like mechatronics. And yeah, and so I basically ended up writing my diploma thesis on self-reconfigurable mobile robots, kind of individual robots that can connect themselves together, form a bigger organism that can then, cross an obstacle or crawl up some stairs. And from then on, I decided, okay, yeah, robotics is definitely my thing. I guess I will never be bored doing robotics for the rest of my life. So I said I'll pursue a PhD in robotics, went in a little bit of a different field, went into surgical robotics, and entered a big collaborative research project between my home university, the KIT in Karlsruhe, Germany, and the university hospital in Heidelberg, a very renowned hospital related to university there, together with the German Cancer Research Center. And basically what I was investigating is how can I capture the knowledge that the surgical assistant has and transfer that to a robot through machine learning and robotics methods. So it was kind of at the intersection between robotics and machine learning at the time. It deep learning, reinforcement learning was already going on, but not yet as dominant in the field. So I used different methods actually, but it was really interesting. So I did my PhD between 2013 and 2016. So of course, neural networks, or the revival of neural networks and deep learning was already there, but especially deep reinforcement learning wasn't going as strong yet for robotics. And an interesting challenge in surgery is actually that you do not deal with big data, but with very little and very sparse data. And yeah, so I went into a totally different machine learning regime, basically used classifiers, supervised learning, and transformed that into a continuous process through adaptive sampling of the classifiers. So yeah, without going into too much detail, but the great thing about this experience was working with people from a whole different background. So surgeons and in general medical staff, they know a lot of things, but not necessarily robotics. And cooperating with them and trying to build a system that is useful to them, that is something that has stuck with me since that time. You know, taking a different point of view on the product you're developing or the research you're doing than your robotics view. So yeah, that was kind of the journey until the end of my PhD. Then I worked for Google Research for a couple months as an intern in what was the Replicator project at the time. You know, when Google had bought up all those robotics companies, including famous ones like Boston Dynamics and so on. And then I came back to Germany again, founded a company with the name of RoboDev. We built modular automation. So basically, yeah, it was somewhere on the intersection between modular robots and classical machine automation equipment. So, actuation modules, linear axis, rotationary axis. And we really focused on ease of use, trying to give it into the hands of not robot experts, but basically an industrial mechanic that can, in the spirit of lean automation, really do their own small scale automation solutions, not going to the high tech end, but really simplifying things. And yeah, I was there then for 4 years, ran that company. For internal reasons, I decided to step out of it in mid of 2020 and then joined ABB Robotics, where I'm in the role of chief software architect since the beginning of 2021.
What does it mean, chief software architect? Like, what is that on a day to day, or what kind of tasks are you responsible for?
Yeah, that's a good question. So when I got this role, it was a new role just set up in the R&D department, and this question also came up. Of course, how do we define it? What is an architect doing if you already have empowered teams that develop parts of the software stack? But what I'm basically doing in my day-to-day activities is making sure that there is best practices across the software stack. And I think some of that we might be talking about later on when it comes to software engineering practices, when it comes to DevOps, when it comes to doing good design, and also following the rules of the game. But the main part is really coordinating from low level software, let's say embedded firmware for a motor control, to the software running on the main controller, which goes together with an engineering desktop tool, which goes together with your teach pendant you use for the operator, which goes together with your applications, your smart robot cells, and also finally with cloud services, telemetry data, predictive maintenance, and so on. So it's a really great role, because you see kind of the individual bits as they get written down into the register, but you also think about, oh, how can I scale my Kubernetes cluster across and replicate data across several data centers to be close to the customer and have low latency and so on. So it's really about software engineering on the one hand, because we have a lot of software that originates from the 90s, has been continuously developed over 30, even nearly 40 years. And on the one other hand, you're building brand new systems, and yeah, how do you bring together the asset you have in your existing software without it becoming a legacy and dragging you down.
Yeah, that sounds really hard. It sounds like all of the challenges of like regular software engineering, plus you have the robot component and network issues and all sorts of things like that. Sounds like very interesting. It sounds like you have to be, I mean, doing the PhD and all of your experience in several areas of robotics. It seems like you like know a few things very deeply, but then you have to know a lot of things like across that whole spectrum. You have to understand cloud things with Kubernetes and like all of the towards the embedded side and everything else. Like there's very much going on there.
It's definitely a rather broad role, and in order to I like to be in the details and know what's going on and having meaningful detailed conversations with all developers. But of course you have only so much bandwidth available. You cannot be an expert in low level FPGA programming and in Azure and Google Cloud and AWS at the same time. So of course, I rely on my team of what we call the lead architects to go, to be a little bit more focused, still rather broad, but yeah, so that it basically, cascades down, and you have your experts that are the individual development teams on the one hand side, and on the other hand, you have those trying to bring the end to end and big picture into all of it.
So it's like a big pyramid where you are kind of the like you help with the holistic thinking and you have knowledge of all these areas and you have experts who come to you and that they have teams beneath them, maybe with experts in them, and it just keeps going down until you reach the people doing the most low level part of the project.
Exactly. So it's basically being finding a good communication pattern, because if everyone communicates with everyone, we are quite a sizable R&D organization.
How
um,
large? How many people kind of beneath you
I
at
cannot
the
say exactly, but it's in the hundreds of software developers for the core R&D, and beyond that, you have a lot more people. I guess it is in the thousands writing application software for customers. But my scope is really focusing on the core products that everyone is using. Like in ABB robotics terminology, we have our robotware, which is the robot control software, the real-time part, making the machine move. We have our desktop engineering software called Robot Studio that includes simulation capabilities and robot cell engineering. And we have something called connected services for the cloud part, basically. And of course, all of those are extensible, and they are extended then by our application engineers. But that's where kind of my area of responsibility starts to fade out, and I leave it then to to our individual businesses to build, a
the
great welding cell
COO
or an
and
automotive
CTO and
line.
this kind of thing?
Yeah, exactly.
Mhm. That's awesome. So it sounds like to me you're building kind of the core that people build off of for the application related software or related products. Ah,
Think of it as, no matter what you want to do with an industrial robot, you need to be able to command it to perform coordinated motions. But whether those motions are then used for 3D printing, for logistics applications, packing totes from A to B, or for assembly, machine tending. Of course, that is then the robot application expertise that comes in at the later stage outside the core, as an extension built on top of it.
how did you how did you choose to work at ABB for this? I assume you had plenty of options. What about ABB was really interesting to you? And actually, it'd be great to give like an overview of ABB and what kind of products you guys work on.
So historically, ABB Robotics has been one of the first robot companies at that time called STA. So ABB was a merger, I think 25 years ago, between a Swedish and a Swiss company. But the old name was of the robotics part was STA, and they basically have build one of the world's first, fully electrically controlled robots. So that we are really talking about the 70s here, so way back in time, and have remained over time somewhere among the top two usually, or the top three. Market share is always going back and forth a bit with the other big robot players. Um, but I would say today we are somewhere around number two worldwide, depending on whether you count revenue, installed base, number of robots sold. So what is your metric to define the global leader? But yeah, so it's a huge industrial robotics
Who's
company.
the other one? Is it Kuka or is it?
So
I don't
KUKA
know
is
too much in
definitely
the.
one of the other ones, Fanuc. And then when you look into industrial robotics, of course, there are a number more like Yaskawa, Denso, Stoibli. So there's a few, but I would say the big three are that usually people look at is Fanuc, ABB, and KUKA. And I've already said industrial robotics, so meaning robot manipulators, from small to medium sized to very large ones. Now, more recently, of course, ABB is also going into collaborative robots. And about a year ago, a little more than a year ago, ABB acquired ASTI, which is a company for HEVs and AMRs, so mobile robots. And so the field of being only focused on industrial robotics has been expanded last year to include mobile robots and mobile fleets. And then, of course, we are also looking into synergies. If you have a broad portfolio of robot manipulators, you now have a broad portfolio of mobile bases, then you can also combine them to create mobile manipulators. But right now, of course, the majority of the company is industrial robot manipulators, but now more and more also mobile robots for intra logistics and logistics operations.
Hmm. Gotcha. And then why did you pick to after starting your company? Why did you pick to go to ABB as opposed to any other alternatives that you had open to you?
So I think what attracted me is the that ABB, in contrast to some of the other players I mentioned, has an end-to-end view of robotics. They are not only producing the robot, the pure robot, but they are also doing cell engineering. They are solving specific verticals in terms of automotive, electronics, general industry and consumer segment, and also logistics. So they do not just sell the robot manipulator together with a controller, and then you need the system integrator to make something valuable out of it, because a robot, if you just have a robot arm, it cannot do much. Perhaps if you add the gripper, it can do a little bit more, but usually you need the whole cell around it, with process equipment, with all the additional peripherals to do useful work with that robot. And ABB, in contrast to some of the others, is not only doing that together with external companies, but is also strong in doing their own application cells, and going all the way up to basically smart systems where you have an entire robot assembly or welding line, and you also take care of the logistics, let's say for car body assembly. So it's, yeah, they do not stop at the robot, but also go into the application, and that I found quite interesting, because I learned the hard way, and also in much detail from my own company, that the difference between having a robot that works, or in our case a modular building kit for robots, and having productive, reliable robot applications, there is a big gap, which is your domain expertise and really knowing what the customer needs. Sometimes you need to know it a little bit better even than the customer, in terms of of course they know their product, but they might not be aware of the best way to process it, to assemble it, to machine it, and So this expertise in really deploying robotics. Yeah.
Like robots who might do things differently, and therefore you have to change the process a little bit. So you have to abstract the idea of what you're trying to do and then adjust from there, given the constraints of your robot.
Exactly. Yeah. Yeah. You cannot simply automate or you cannot take the manual process and just put the robot there. I think a good description I've often heard in the past, it's not as true anymore as it used to be, but still good enough. Imagine there is a factory worker doing some assembly task, and now you put a classical industrial robot there. And a classical industrial robot doesn't have a lot of external focus sensors. So, it is position controlled. It might have some force torque sensor integrated, but it does not necessarily even have a camera attached to it. So it's basically blind. It has only one arm, and most grippers are two finger grippers. So the gap between a human, not just with its intelligence and but also with its visual perception skills, with its reasoning skills, with two hands that are very flexible and are able to do fine manipulation and everything. And then you go to one arm that's blind and basically only has a two finger gripper. There's just such a big gap. So usually you have to reconsider when you go from manual process to an automated process. Well, how can you make that work under those constraints you have with traditional industrial robotics? Of course, the times are changing now. We are seeing more and more what used to be pure research in academia, like making much more use of cameras, 3D cameras, and tactile sensors, force torque sensors, going to more complex end of arm tools, more complex grippers. So it's slowly diffusing into practical use, and that will change a lot of things soon. But historically, yeah, you you had your two fingers, one arm, and no eyes, so that was quite hard.
That's crazy. How much of, so I'm struck talking about kind of this the blur, like you have academic research and it's becoming more and more useful and used in manufacturing or just, I don't know, general robotics applications. How much of your role as chief architect is understanding where things are going and trying to build with the new tools that are becoming available or the new methods or the new practices, all these things?
So that's a very important part. Of course, nobody has a crystal ball and no one can look into the future and see exactly what's coming our way in terms of demands on a piece of software that you create today. But of course, there are mega trends, there are tendencies, there are technological, let's say, pathways, and it definitely is an important aspect to trying to figure out together with of course the business, together with the customers, together with product management, if we build this today to satisfy today's needs and build applications based on what's possible today, but we see on the horizon, it's, let's say, 3 to 5 years from now, a technology that is still in more on the research side, that is still mostly talked about at conferences, will become productive. And if that happens, are we ready for it, or do we have to redo everything we are doing today in order to accommodate this new technology or this new software solution? And so I think striking a balance between not over engineering things, not building the universal platform that will never be used on the one hand, but on the other hand also not being myopic and just building what you need tomorrow and then you have to refactor everything. That is definitely one of the big struggles. So some people say architecture is all about trade-offs, and I think this trade-off between doing just enough now but also keeping open for modifications down the road is one of the big trade-offs. And there's no silver bullet to doing it right. Perhaps it's a mixture between experience and seeing what's happening around you. But you are not always correct, of course. So building your software in a modular way, building it in an extensible way, I think that's one important way how you can deal with an uncertain future. If you build one big monolith that you have to basically scrap and rebuild if you were wrong in predicting the future, it's a much worse situation than when you build in some architectural runway in terms of, okay, I might have to replace the subsystem here entirely, but I can just reconnect it to everything else that I have built.
Yeah. So then this gets into a lot of software engineering ideas to me, where you make things as independent as possible. So you can make it modular and you can substitute things out. But I imagine or I guess I'm just curious about what kinds of heuristics you have now for designing, I don't know, a robotic software architecture that you found to work really well.
So I think everyone in robotics is aware, of course, about ROS these days, and not just since yesterday, but quite a few years. And I think that has inspired many people, both in academia as well as in the industry, to rethink their approach to how they build robot software. Because historically, robotics has been seen as part of embedded software engineering, and it's close to how you would build machine control, a CNC control, perhaps even software for cars. And I don't necessarily mean autonomous vehicles, just regular, good old cars with their electric control units in them to control the windshield wiper and the engine and everything. So it was really focused on being resource efficient, on making good use of your resources, your compute resources, your memory. And now there's a shift that is starting to happen, because if you build highly resource efficient software, it's not necessarily very flexible software. And the question is, which of your so-called non-functional requirements, or I prefer to call them quality characteristics. So what is more important? Is it performance? Is it resource efficiency? Is it reliability, safety, security, maintainability, portability, flexibility? There's a lot of those alities, and you cannot maximize for all of them at the same time, or at least no one has yet found a method to do that. So you need to kind of decide, am I building a highly resource constrained system, and then I might have to let go some flexibility, or do I make use of Moore's law, that's still going relatively well, so CPUs become more powerful, or I get more cores, I get more memory, I got more disk space without cost increasing too much. And do I make use of those for emphasizing the resource efficiency a bit less, and putting more emphasis on flexibility? And I think this idea of going to a more service based or even microservice architecture, ROS style, where you have your nodes that communicate with each other through defined standard messages, is a direction that provides this flexibility that at least I believe we will need in the not too distant future. Because historically, robotics was a rather vertically integrated industry, kind of like IBM in the old days. So you had the robot supplier that was writing all the software, that was providing the hardware, that was providing the application. And this is definitely changing, because like in the bigger software world, one one supplier, one company can simply not cover everything on their own anymore. Imagine iOS or Android, if only Apple and Google would be providing the apps. That wouldn't fly as well as when you have a platform where others can add value, and especially can fulfill niche demands. And these niche demands need extension points basically in the existing software. And yeah, and all of this drives towards how can I resync my system in a way? It must still be, hard real time. It must still be reasonably resource efficient because cost is a big factor in robotics. But I also want to have it more flexible. So this is kind of the general idea, I think, coming in from web software, coming in from desktop software, that you just think very hard about modularizing and being able to compose new variants of your software in a much easier and lower effort way.
Do you think so? Microservices in kind of a ROS context might be like, or services might be like a node that does a specific task. Um, do you think so? I'm thinking of like on in web related applications where they have like serverless and this kind of thing, where what they have is best effectively it's a function that runs out somewhere on the web. So it's stateless. You pass it input, it does something, and then it returns the result to you. This could be like cloud robotics. Do you think robotics will start going to this direction, or will we stay with kind of the ROS node running locally or running on some computer nearby, but still in the same network?
I think that's a really interesting question. So this topic of cloud robotics has been, I think that term was coined about 10 years ago, perhaps a little more, of this idea of outsourcing some of the computational demands that you need for running, image recognition, running some kind of compute intensive big neural networks. You might not want to spend the money to build hardware into the actual robot controller, but rather use it on demand from the cloud. But of course, you always have the challenge of you must be, connected 24/7. So it is another potential point of failure if you build a wide area distributed system as compared to two PCs talking to each other on the same switch locally. There's latency is always a challenge. So my view is that yes, the cloud will play a bigger role in the future for robotics, simply because you cannot. There is a dilemma. Either you build a very capable hardware in each and every robot, and in 80% of your customer installations, it will just sit there and be idle, and then the customer will complain about the high cost, of course, or you need to eat the reduced margin, which both is not ideal. Or you have a
Both, which would be not as good. Yeah,
yeah,
lower
exactly. Or you
margin but higher cost.
go for a lower power device, but then the question is, where do I get the functionality for those 20 or 30% of more demanding applications? And I guess it will be a mix between edge devices and cloud. A lot of industrial robots are still run air gapped. Basically, they don't have internet connectivity. A lot of manufacturers don't want them to have internet connectivity still, for reliability reasons, basically, and reasons of trust and cybersecurity. But I think, step by step, it will become more and more normal that at perps, you don't have to put your whole controller into the cloud. That idea has also been around and is still around. You use 5G or fast, fiber optic internet connections, and you then have a really low latency connection to some data center close by, and then you even run your motion loop in the cloud. I don't see the big benefit of that, because motion is relatively predictable in terms of demands. So let's keep that local, but let's put the higher level loops that if you think of it in terms of nested control loops, somewhere deep down you have your servo controller controlling motor torque, position, velocity, and so on. Then you have your control the overall manipulator posts doing basically path planning and trajectory following. So I think that will stay local. But then above that, defining where should the robot go and what is going on in the environment, I think there will be some. We will see it either running locally on the edge or going all the way into the cloud.
Yeah, yeah, that's very interesting. And I feel like if it's running on the edge or in the cloud, that gives you flexibility because you're hardware constrained, you're power constrained, you're all sorts of space constrained with your robot. And so, therefore, it's not easy to add more hardware to do more computation. So, what you could do is you could just have that robot send a request somewhere and say, hey, what's in this image, or what's my higher level direction for this next task? And then it's lower level control loops manage fulfilling those. Drive over here, fly over here, pick this up, whatever it might be, this kind of thing. Seems like it's more flexible.
And the interesting part, the interesting part is, of course, that you need to design your software so that this is a deployment time decision, so that you can be flexible in where you run your software, because it doesn't come for free. If you build software for your robot controller that cannot necessarily run outside the controller on an edge device or in the cloud, and perhaps there is no way, if it would be able to run outside, how it can then talk to the rest of the system. So building a system that it can be distributed, that you have components that are flexible with respect to how they talk to the rest of the system. I think there's also this relatively recent project Focross, which is also looking into, I think, this very aspect. Yeah, and but it all starts with the idea, my individual robot capabilities, my functionality, my services, my nodes, they are flexible with respect to how they communicate with the rest of the network, and I can simply configure what node talks to which other node for this specific application. And this might sound relatively trivial if you are a software developer coming from web background or from general software development, but if you come from this embedded software world, this is a relatively recent development. Also, if you talk to people from the automotive industry, there is also this big shift happening from people thinking in terms of small hardware devices that each one runs highly embedded software, to thinking of basically running a Kubernetes cluster in your car, spread over 2 or 3 very powerful PCs. And and this shift is really, I think, undergoing, especially for those that have been around before Kubernetes or even containers or even virtualization was a thing.
Yeah. Do you think so? It strikes me a lot of this is coming from kind of the web community where they're trying to deploy resources evenly and manage all the requests and this kind of thing. So then you have Kubernetes, and I haven't used Kubernetes. I've done quite a bit of Docker and Docker Compose and things, but I think it's like basically for managing deployment of large networks of devices or specific runtime things, kind of like Docker Compose does. Is that fair?
So I would say the main difference might be that when you look at so it's basically the cluster underneath Docker that allows you to just tell it, oh, I would like to have 5 versions of this container running, and I would like there to be a reverse proxy or some load balancer gateway that talks to each of them. And so I think it's a bit similar to the old Docker Swarm, but of course technically a much more sophisticated solution.
Yep. And so that's a thing by Google Kubernetes that does that. And so it's effectively it lets you like load balance on a bunch of machines the requests that are coming in. So I have 5 computers and I have a website up that runs something. And you're going to have your load balancer on top that's going to pass it to each of the machines, depending on how you're doing your, like if you're going serverless, you don't really need this. But
Yeah, that's an interesting idea actually. So this whole topic of virtualization, containerization, and then flexible container deployment, I think that has been well received now in the robotics community. The equivalent of serverless for robotics, of course, you can run robot related functionality in that way in some cloud, but putting that concept down to the device or to the edge, that's an interesting thought I need to pursue after our after our discussion.
Yeah, it seems really cool. It's so like I feel like in robotics, we touch so many technologies that we're often not leading in any of them. And so we're kind of following the best practices of these different communities. And I've been playing a lot with web things because I'm interested and I'm very interested in the connection between robotics and web. And so it seems like one of the big ideas in the web community is edge computing and serverless and these kinds of things. So edge computing, having a bunch of devices everywhere that are small, but you can delegate work to, and they can be very close to the whatever the thing trying to access them is. So that's a big advantage. You don't need like big data centers everywhere. But so I'm seeing all this serverless stuff, which is really interesting. And all I understand it as is a function that's going to run somewhere. It spins up effectively like a Docker container. And then that Docker container puts the data through, runs a function, returns the result, and then closes down, which is highly, highly flexible. And then you don't have to do all this load balancing that you have to do with like Kubernetes. But I may misunderstand that.
No, no, I think you're definitely definitely right. The question is how much in your usual robotics stack is completely stateless, um, because you're, if I think of ROS, a lot of nodes require the an updated transformation tree, and so you might at least need some stateful version of serverless, but that also exists. So
Yes, totally. Or just keep the instance up for a bit, close it down later, this kind of thing. But also, I mean, matters of perception, things like this. Like if you wanna run around a house and detect objects, this could be a function that is just run. You pass the image up, the image gets analyzed, and then it returns the coordinates of things that it sees. Like that doesn't really require state. And I imagine a lot of other perception tasks would also be similar. Like what's the pose of the human or this kind of thing.
yeah, another topic is, of course, there is the aspect of what happens, kind of, I like to call it in the loop. The robot is moving, it's running its application. And then you always have the topic of real time, of latencies, of jitter. But quite often your robot cycle looks a bit like that, the robot is, let's take a simple case. You're doing machine tending, you're picking raw parts out of a box, putting them in some, let's say, CNC machine. They get work done, and then you take them out again, or need to, take them out, turn them around, put them back in, something like that. And so, of course, while the robot is moving, it is essential due to the laws of physics that your control follows very smoothly, very deterministically, its timing constraints. But if you need to figure out, oh, where is the part, or how exactly should I grasp it, that that is usually a moment when the robot is standing still for a little while, or you can do it kind of while you're moving. You can think about your next move, and that can be a situation or an application where you really can leverage scalable resources. Let's say you spin up 100 different simulations of grasping the part in different ways, and then you return those that were most successful. Same goes, of course, for object recognition. So not everything needs to run at the 1 millisecond, 10 millisecond, 100 millisecond hard deterministic cyclic loop. I think those higher layer functions in the robot, or capabilities, they could really benefit from flexible compute that you pull in from wherever it is available.
Definitely. Do you think do you think there's going to be more of a merging between robotics and web because of this? Because I mean, it seems like we're adopting, especially if you're going onto the cloud or edge devices. It seems like we're trying to take a lot of what exists, or a lot of Internet of Things kind of ideas. Do you think there's going to be more of a merging or unification, or us using the tools that these communities typically use in the robotics space?
I think yes. So there will still remain some differences between robotics and other types of software. Um, and perhaps robotics even drives some innovation in other fields. If you think about real-time middlewares as opposed to best effort middlewares, or guaranteeing certain things, or making things deterministic, and so on. But of course, in general, robotics is I love robotics. It's a great field, but if you look at the size of it compared to software overall or web software, it's a tiny niche. And if if I remember correctly, we mentioned Kubernetes earlier, and it's one of the biggest in terms of most contributors and lines of codes contributed, one of the biggest open source projects now. Or otherwise, we can of course use the example of Linux. The robotics community would never be able to sustain building a solution like a Linux. It's just too small, too few developers, not enough budget, to put it like that. But of course, we can leverage those technologies from the bigger software and open source community. And I think Linux is actually a great example. Um, Historically, Linux was a pure general purpose operating system. Everything was optimized for throughput, and nothing was optimized for real time, low latency, low jitter, deterministic execution. And then about 20 years ago, someone came along and said, okay, can we make Linux a real-time operating system? Perhaps, you don't want to control your servo motor with it directly, but for, let's say at the millisecond level instead of the microsecond level. And then there was this huge RT patch that was developed over 2 decades outside of the kernel, and it was several megabytes of source code patch that you had to install and build your kernel. And it was always a bit painful, but you could successfully then use Linux in industrial automation and in other real-time fields, and of course also in robotics. And now over the course of time, people managed with a lot of effort to put more and more of this functionality into the vanilla kernel. I think the current real-time patch is just a couple thousand, or perhaps a few 10,000 lines are left. So the majority of the functionality has now been merged to the standard Linux kernel. And interestingly, it is used now outside industrial automation and robotics, also for web services. For example, video conferencing, where you need low latency and some determinism, and so on. So what I want to say is, robotics needs to build, on the shoulder of giants of the general software industry, because it wouldn't be able to do it on their own as a community. But at the same time, its very special needs often lead to improvements then in the bigger software community. So I think that we will seek to continue.
Hmm. What are some areas you think that would occur in?
So um, if if you consider autonomous vehicles as a part of robotics, which I definitely do, of course it's a very specific subfield again, but if you look at everything they are doing with respect to simulation, and also photorealistic simulation, or large scale simulation, um, that will, I think, also perhaps have an impact back on the gaming industry, where these most of those simulators originate from. I think some AV company actually trained their cars in a computer game in the beginning, when there was no autonomous vehicle simulator yet. So I think there is this, using the big technology that is available, adapting it, but then also feeding back some of the learnings and improvements you have. And I guess in the whole area of AI and machine learning, and especially in particular reinforcement learning, robotics and machine learning usually has the challenge of, if you do not use simulation, if you use real robots, and sometimes you need to, you cannot do a whole lot of experiments. You cannot collect, thousands of data points, or run thousands of episodes. And of course, that drives the robotics research community then to ask, what is the minimum amount of training data I need, like few shot learning or even zero shot learning, and or using transfer learning approaches. And that will of course then benefit the wider community again. So I think this back and forth will continue, and it will be particularly strong in in the area of middlewares, or flexible compute network fabrics, basically adding the real time and reliability aspect to it, and in the question of simulation as well, and reinforcement learning. I think those are three areas where robotics will use as much as we can from the wider field, but the results will greatly influence back what is happening outside of robotics.
I feel like I've been involved in robotics for roughly 10 years now, mostly in academia. I feel like the community, especially going to like ICRAs or IROS and these big academic conferences, the size of the community seems to have grown tremendously. And you mentioned it's a small community now, especially compared to like the web community or I don't know, general software engineers. Um, how do you think it's gonna? I mean, how do you think it's going to grow in the future? Do you think it's going to keep growing? Do you think it's going to be like an exponential growth as robotics becomes more capable and you see more companies? So like there's more need for flexible solutions, more roboticists. Like, what do you predict for kind of the growth of the robotics community?
So my prediction is that the established robotics, industrial robotics, logistics, AMRs, autonomous vehicles, they or partially autonomous vehicles, they will continue and grow a healthy, let's say, 3 to 8% every year. Um, the explosion of this market or this community, I think, will happen in where we do not have robots today, but everyone looking at what's happening there, what jobs need to be done, uh, immediately thinks, oh, couldn't that be done by a robot? But the answer is no, not yet. We are still lacking, the either the sensor processing or the robustness or the planning or reasoning capabilities or the fine manipulation or whatever it is. So I think we will see a substantial growth over the next decade in especially in service robotics and professional service robotics. Industrial robotics will grow. I think that one will see perhaps a new growth spurt outside the applications we can already do since 10 or 20 years. So I don't think we will install many more welding robots. Yes, of course, it will continue together with the industries, but using robots that fundamentally require image processing and real-time reasoning, real-time path planning capabilities, not just following pre-programmed motions, that will unlock a lot of potential. And also, if we make robotics more accessible, like the I mentioned the mobile industry, mobile phone industry earlier. You also saw a big shift there when it went from feature phones that were relatively locked down, and a bit uninteresting also in terms of what you could do, to going to smartphones and the whole ecosystem around it. So of course, if you consider robotics being driven by software, or intelligent robots being driven by software, um, the overall software community will always stay bigger than robotics, because one is a superset of the other one. But its percentage will definitely grow. I'm confident that in 10, 20 years down the road, there will be robots around us and not just locked away into warehouses and into manufacturing facilities. And somebody needs to build those robots, somebody needs to give them capabilities, and that will lead to a much bigger software community around robotics as well.
So I've heard the smartphone metaphor quite a bit in robotics. So it's like um, when you get that first iPhone or smartphone, now we can build applications for, or when they introduce the App Store more specifically. Now developers can make applications. Now their usefulness explodes because people are making applications, solving the niche problems that you mentioned, and also doing things that Apple or Google don't have the time to invest their own resources in. With robots, one thing that's interesting is that, well, I mean, like a smartphone, the form is fairly clear. It's a touch screen. It's a small brick with a touch screen on it. Robots like a mobile manipulator is different than something that can like so you have an indoor one, then you have a legged robot that can do stairs, and then you have one that can traverse outside, maybe in like the woods or snow or this kind of thing. They can have many different form factors. Do you think that there will kind of be like a few general robots that kind of kick things off, or will it be like how will robotics do something kind of or I don't know parallel to what the smartphone industry has done?
I guess one of the big challenges is that no one has yet found the equivalent of the universal Turing machine in robotics. So there is no universal physical machine. If you want to have exert high forces, you need the big beefy robot that's very stiff, has big motors. If you want to be safe around humans or you want to be compliant, then you might more go for lightweight structures. If you want to traverse rough terrain, it's perhaps not ideal to have wheels, then you might want to go for legs. So I guess in terms of its physical appearance of the hardware underneath, we will keep a large diversity of robots, even if at some day humanoid like robots become economically viable, become more robust, become more capable. It's still it's like the saying, planes or airplanes don't flap their wings. So there we went for a different solution. Also, we the an excavator doesn't look like a troop of people with shovels. It's and so on. And a car does not have very long legs but wheels. And I think due to the physical reality, there will not be the universal robot. Rather, you will have different robots for different use cases. And perhaps if we make it to the Rosie, to the home robot, that might be a humanoid, for the simple reason that we have optimized our houses for humans. We are living in them. It's not the natural place. It is purposefully designed to be comfortable for humans. If you look at, for example, a staircase, the height and width of the stairs is adapted to the average human size of their legs and so on. So I guess for home robots, long-term humanoids actually make sense. When I look into going into a warehouse or in professional service robots, why should a robot for cleaning floors look like somebody with with a swiper instead of like they actually look. um, so I think from the hardware we will have this diversity, and it definitely makes things somewhat harder than when you look at smartphones. If you talk to a mobile phone developer, they will tell you about all the excruciating details, what makes it hard to develop apps that work across all phones. But from a taking a step back, it's basically always a multi-touch screen, and you have your networking capabilities. So it's much more similar than the diversity between a drone and a humanoid and an industrial manipulator. But looking at it from the software point of view, there it might be different, because if you look at let's say computers, from your microcontroller, your laptop, your desktop machine, your two socket server, your I don't know how many GPU supercomputer cluster, that's also quite a different form factor. You know, a supercomputer is not a million smartphones connected together or a million Raspberry Pis. It's built quite differently, and but still we consider all of it software. And at least on the level of the operating system, on standards like POSIX, containers, and perhaps programming languages, we have achieved some standardization and some universal ways to go about it. So yes, programming supercomputers is quite different from programming microcontrollers, but it's also not something entirely different. And I think this um, marketplace for, or this app store for robots that many people have envisioned, and so far we all have failed to build it, will become reality simply due to um, finding finding the right level of abstraction. You know, kind of this notion of skills or self-contained robot capabilities that you can deploy in different contexts. And I think Ross is one of the, you know, will be seen down the road as one of the um, triggers for this development, in terms of, oh, you can use the nav stack, and it you can make it run on very different robots by configuring it, by adding plugins. And so I definitely think some platform player will come along, and at least for, let's say, one area of robotics, let's say perhaps one for service robots, one for industrial robots, one for logistics, let's see whether they merge eventually, and for autonomous vehicles. But I think those platforms become a necessity for the industry, because no player is big enough anymore to do it all on their own, and then the market forces will drive it towards converging on, you know, some lowest common denominator of how I can deploy robot software, what APIs do I provide to hook into what others have built.
Yeah, all very interesting. A bit of a digression. What do you think about the Tesla bot? Do you know it? It's like a humanoid by Tesla.
So let's see what they show on their second AI day. I think they moved it to September this year. So you know, I would be, I'm skeptical about it. So of course I welcome every dollar that goes into robotics. So from that perspective, it's not a bad thing. On the other hand, over promising and starkly under delivering might also hurt robotics, similar to how, you know, this, yeah, AI winters, or this recent accident that was reported where a robot broke a child's finger because it was, you know, horribly wrong set up, no safety, nothing. um, the general, you know, perps roboticists, of course, they understand what went wrong there, and how to prevent things like that. But if now the, you know, general public hears about the Tesla bot, then they will build something in a year, and, you know, everything that was promised, and then it becomes the next Asimov, you know, Honda Asimov, great robot, helped a lot for robotics research, but never became a product, was now eventually shut down. Or what Xiaomi showed their humanoid, I think, last week. And it's, yes, it looks like a humanoid, yes, it moves like it, but you and me both know that this will not become a something more than research. It will never be at the price capability point where anyone would want to use it. So, you know, I welcome a company like Tesla, of course, going also into you know, non-autonomous vehicles robotics and investing money there. That's good for the whole robotics industry and community. But of course, the way that you know, Tesla and its founder or its CEO goes about making announcements and not always delivering, or at least not on the timeline, that might then again hurt robotics. So I have mixed feelings about it. Let's put it like that. But I'm definitely excited to see what they were able to put together within a year.
Yeah, I don't know. The thing that is interesting, so like autonomous cars, I've been skeptical of for a very long time. Like when the initial research or public announcements, like 2018, we're going to have self-driving. I was working in self-driving, and it was like, no, no, we're not. Like I'm fairly confident it will not work. Um, but the thing that I've really seen from it, which is cool, is there's been a lot of investment in the area, which, like you're saying, every dollar is good. But so it brings down the price of motors, it brings down the price of like Validyne sensors, LiDAR. It brings down the cost of a lot of things. Spin-offs like Foxglove occur that came out of Cruise. And I think that these are tremendous value adds for the community that kind of they lower the difficulty of other robotics tasks, so then more robotics can occur. I wonder if Tesla Bot will be similar because it's a big company throwing a lot of weight towards that, perhaps. Like, I don't know how much they're funding it or how much they're investing in it, but they made a big splash with their announcement for sure.
No, and also another positive side effect is that it puts it higher on the agenda of venture capital firms. So we might see startups that can be funded that wouldn't have been able to get started without a certain, hype and promotion around it. So yes, let only time will tell whether the positive or the negative sides of this one have the higher weight. But it was definitely a surprising announcement last year. And I guess I think even on IEEE spectrum captured the sentiment of the general robotics industry relatively well, saying, I've been in this for 20 plus years. I know it from the bottom up. I know what we have in our drawers, what is published or what is going to be published soon. There's no way to deliver the capabilities that were promised in a few years. So I think the timeline is totally off. But if they invest enough, and perhaps that leads to some follow-up investment and others looking into it, then we might get to it much faster than if they wouldn't have gone out with the announcement. So yeah, I'm German, so I'm kind of technology skeptical by birth. But then on the other hand, I try to be optimistic about developments, especially in robotics. So yeah, let's see. I'm trying to look on the bright side of it.
Mm-hmm. One other area. So you mentioned middleware and real-time operating systems, simulation and reinforcement learning as areas that robotics could be growing in and kind of contribute back to other communities to help general software engineering or general software. What do you think about human in the loop setups? I've been seeing a lot of these companies through doing this podcast where it's like they solve a problem 90% of the time, and then they have a human that watches over and solves it when some exception pops up. Um, I feel like this is a fairly large direction that I'm seeing startups, especially as robotics is moving into less and less structured environments. So then you come up against these, I don't know, 1% things all the time, and they're really hard to generally solve. But what do you think about this area of robotics?
So I'm sure it's an important, piece of the puzzle, and especially as a transition technology to fill the, all those strange 1% long tail outliers that usually happen in the real world. I think the autonomous vehicle companies have experienced a lot of them already. The more we are making other types of robots flexible, the more of them we will also see there. And yeah, as you say, going from 99 or even 99.9% to 100 is still a long way. It gets exponentially harder and more difficult to even find those rare cases before they happen in production. So I think, for some system, it's relatively simple to implement it. Let's say you have a robot doing item picking in a warehouse, and it can identify 99% of the objects, correctly grasp them, perhaps retry in a sensible way if it fails, but then it might get stuck. And then if that happens rare enough, having someone that locks in, uses their human skills and world understanding to fix it remotely, and then the robot can continue, that might unlock applications that would otherwise not be possible, because, well, if it stops and you need to have an operator in the shop floor or in the warehouse come along and fix it, that will soon become an operational nightmare, and customers do not want to make use of it. Or the overall equipment efficiency, the OEE, will just go down to a level where there's no business case for it anymore.
What's
So I
that?
think
The earnings, or what was that acronym?
overall equipment efficiency, it is basically, if you think about the equipment would run at full speed and full utilization, what percentage are you actually making use of it? Sometimes the machine needs to wait for other machines, and it's one of those typical dashboard numbers I see in many manufacturing operations. So yeah, I think it's an important contribution, but, and now comes a big but, I would not be happy to see too many players in that field, simply for the reason it kind of avoids dealing with the hard problems we still have to deal with in robotics. If you end up then remote piloting a large percentage of the time, um, I think that's happening with some last mile delivery robots. If I remember some news stories correctly, that will not scale. So yes, it is an important bridge to unlocking certain technologies if it's possible to put an operator there with before something bad happens. Um, but it's also one of the perhaps easier problems that is not so much robotics related. It's not, yes, you need to be efficient with bandwidth and you need to do a whole lot of other things well to have a good remote operations solution. So it's not an easy task, but it doesn't solve the robotics problems of making it more robust, making the robot more self-sufficient, more autonomous. So yes, it's good that people are there, but I hope that there is also a large percentage focusing on getting the 98% to 99%.
Definitely. One thing that is clever about it, from my perspective, is that you also are generating data. Um, so if you say you have a person teleoperating a robot to do simple around the home tasks, you generate all of that data, and then you can use it in like a reinforcement or some sort of machine learning context to try to actually do the top. If we're relying on machine learning, it could be a way to generate data for accomplishing that task.
Yeah, that's true, because it also makes it easier to, if you remote control the robot and you record that data, that's much easier to learn from than if a human performs a task with a different morphology, with different hands, different arms, different other capabilities. So from that, but still, if you do it to bridge the gap while you cannot perform it, and then your ultimate goal is to automate it more and more. For me, that's a more interesting goal than saying, okay, we try to make a business case out of doing teleoperation all of the time. Yeah.
Yes, for sure. Yeah, if you're saying I'm just staying, I have none of the companies that I've interviewed has been the permanent model. The model has always been a like basically a stand-in for those 1% events that throw them off, with the goal of using that data to automate eventually this kind of thing, or decrease. So it's like the grocery store kiosk model, where maybe kiosk isn't the right word, but the self checkout ones where one person is manning 4 stations, and then they want to make it one person manning 8 stations and 16 and 32 and da da da, on and on and on until it's really really scaled well, because you have one person handling these incredibly infrequent events, and thus they can watch many robots, this kind of thing.
No, I think for that, it's definitely valuable and also needed, because the alternative is that the solution doesn't work at all. It would then be stopped too frequently and not be a solution.
And that efficiency metric you were talking about, where it's not running very well. Um, with this, So we have a lot of things are going like using reinforcement learning, where they have kind of like an objective and they're trying to maximize it, and they learn um, how to do it better. With this, in the applications that I've seen, well, I guess more generally, what do you think of this? And then I'll say what I'm seeing as like an interesting dynamic in this area.
Using reinforcement learning in particular.
Yes, in a robotics context to solve various problems. Maybe it's locomotion, maybe it's picking up stuff, maybe it's, I don't know, anything else.
So I guess there are two fundamentally different viewpoints on in general machine learning and in particular reinforcement learning in robotics. One group that I count myself part of says let's solve those things with classical engineering, no, let's say dynamics and kinematics and all the fundamentals of robotics. Let's solve that with known engineering methods because we can give guarantees for them and they are not that hard to apply once you have figured it out. And let's leave machine learning, reinforcement learning for where we do not have a grasp on how we could even engineer it properly, where you either have you're modeling tasks that how do you describe opening a bottle and pouring a glass of water or cleaning a table or doing other high interaction tasks,
Especially
because
with like a lot of contact forces and things that make it very hard to model wetness if you're cleaning a table or
the simple engineering solution that was tried for a long time doesn't work. There's just too many parameters. There's too many things where your models are thrown off. So for everything where you do not have a clear way forward using engineering solution, or they end up not being robust, I think this is a great opportunity to make robots more capable. Where I have doubt is doing the whole end-to-end learning. I think it's intellectually really interesting to say let's put pixels or RGBD data into a neural network and get motor torques out of it. But it's unless we get much better in understanding and structuring deep neural networks, it is just too big of a black box in my point of view. Let's say you end up with evaluating the learned solution and it mostly works, but in a triangular table that has a really sharp corner, there it always fails. what what are you going to do if it's a reinforcement learned model? Well, you're trying to capture that training case as well, retrain it. And it's really hard to debug this whole topic of explainable AI, and it comes into play. And the bigger your black box is, of course, the harder it is to figure out where are the knobs to turn. How can I make the system better in the cases it fails? So I've always been a big fan of saying, let's use an engineered system, a traditional system, with a lot of smaller black boxes that I keep a tab on, where I kind of look at what goes in, what goes out, and I have a understandable system around it, so I can locate issues in a better way. Of course, the argument against this is that if you have a manually engineered system, um, then certain couplings that get learned automatically between different layers or basically different feature levels in your net will not be possible, because you discretize it in between and force it. Okay, here I want to have clear joint positions and they go into my kinematics model, instead of the neural network perhaps kind of wiggling a bit with the kinematics model to do certain things that you cannot do otherwise. um but I think the challenge is, and that brings us a bit to this topic of how do I test my robot, and the whole software engineering that I think triggered our conversation initially. um it's much harder to test an end-to-end learned system and also evolve it, because it's not like you train it once and then you're done. robotics, like other software, is continuously evolved over time. Customers demand new functionalities. There's new business opportunity to deploy your robot into new applications, and you want to have a clear path from what you have to the next capability, instead of saying, okay, then I retrain based on my previous network, and I'm not so sure whether it generalizes far enough. So um, I guess no intelligent robot, no new robot application out there will be possible without some form of learned subsystem of it, some, whether it's object recognition on the perception side, whether it's performing actions and training them through reinforcement learning or other things. But my belief, at least, is that we will also not see end-to-end learned systems in the field so much, but more, no, let's train the gate, a gate pattern for a legged mobile robot. Let's do that completely trained end to end, but on top of it, defining, let's say, the trajectory or the map building. Let's not also pull that into the same network by reading in the laser data or the camera data, but let's make a clear separation and abstraction between these different robot capabilities.
Yeah, for sure. I do think it makes it very, very hard to test if you do an end-to-end system. And I really like that idea of having several black boxes. So you say this is our mobility one. It gets us from here to here. You pass it coordinates. It'll figure out the rest. This kind of thing. Like that to me is really, really nice. And if you do train the whole thing, you never know what it's generalizing to. So like you could train it and then it works pretty good in some cases, and then you train it again on additional data or whatever, and there's no guarantee that the function that was learned with all of that would handle every edge case the same. So maybe you get weird interpolation things where it just does unexpected stuff, and I would imagine that that would be very hard to scale. Um, I don't know, and guarantee good behavior. But I like the idea of constraining it to this is a small box. It does this one particular thing. And maybe in the like really, really distant future, end to end robotics training will be more of a thing. We'll see.
It's most definitely a worthwhile research pursuit to see how far can you push it, and it feeds back onto the bigger machine learning community, and I think OpenAI gave up on robotics, or they announced they will pull out of robotics because it's too hard at the moment. But of course, it let them down, I think, some interesting paths, and they will come back when they have kind of figured out how to either train with robot simulation more efficiently, or or just there are newer methods, and then one tries again. So I think it's, again, robotics is a hard use case uh, due to this. There are several factors in terms of input data and also what your output causes. It feeds back on your input through your environment, and some of these you do not observe in to the same extent in non robotic software, and so that kind of leads to new challenges, and those new challenges then might trigger new insights or new approaches in the bigger field again.
Yeah. Now, moving towards testing a little bit. Now, when you have a system like we've talked about, where you go from the embedded code that's running devices, talking to sensors, whatever it might be, then you have your higher level control logic, then you have your cloud management stuff, maybe databases, maybe servers running and doing some of the computation or whatever it is. And then you have to worry about deployment and all these things. Um, Talk to me about testing because it sounds really, really hard.
So I would start by saying that robot software is software. So what we have learned in the software industry, how we can guarantee quality, how we can have higher productivity when developing it, we should also apply for robot software. So that's something where you need to start with before you think about specific challenges in robotics. First, try to follow the best practices in terms of software engineering and testing that we know about any type of software. You should have a proper testing pyramid, a lot of unit test cases at the very individual function level. You should have some module test levels where you test, let's say, a class or two that interact, or a component. You should have some integration tests, which is all pure classical. I define some deterministic input. I run it. I run the software under test through its paces. I check whether the output matches my expectations. Otherwise, it's a mistake. And I do that on different levels. Kind of, I test differently sized things, because what I can find in an individual function, I might not be able to catch mistakes that happen in the way how functions interact, or state gets built up in some class. So whatever we are doing well in software testing, we should also do in robot software. There's no excuse for not doing it, basically. But then there's also some things that are different from other types of software. And the first topic is really this input data and the expected outcome of it. Because let's think of a simple let's say a vacuum cleaner mobile robot that has some lidar laser scanner on top of it. And the task is to cover all of the accessible floor space. So a relatively well defined task, 2D. You need some kind of 2D slam. And okay, so what's your input data? Well, your input data is perhaps an array of, let's say, 128 floating point values. That is the laser distance. And your output is just two floating point values, the velocity of the two wheels of your differential drive. So, I've seen more complex functions in non-robot software than, a vector resulting in another vector. So it's not so much about just looking at the API. The question is really, well, what is the relationship between this input vector and the output vector? And that's where things become tough in robotics, because usually there is no well-defined relationship beyond the software you actually want to test. So in testing, you usually talk about, you have a test oracle, so you know what is the intended result of running a certain test. But of course, if you talk about the, let's say your navigation algorithm on this vacuum cleaning robot, well, the outcome is I want to cover the whole floor and everything that's accessible. But how do I actually check whether I have covered the whole accessible floor? For that, I already need to employ some form of, path planning. And I think that this is the where it really is different from other types of software, that the input is very diverse, very complex, and the relation to the output is not easy to write down in simple terms. It is basically your expectation of how the algorithm works correctly. And so what do you do? Of course, you can say, I have run the robot in a real environment. I have put some trackers on it, and I checked, yes, it has covered the whole accessible floor. And then I put this input and the output as my test data. But of course, if I tweak the algorithm to cover the floor more efficiently or avoid obstacles in a better way, then all my tests will fail, and I will be very sad, because I have to redo all my tests, and I do that twice and then never ever again. So yeah, what is a possible solution? And I think a possible solution, and this is what I wrote about in this robot unit testing paper many years ago, or well, that many, about 8 years ago. We have, what can we do to create create input data and have a test oracle for the intended outcome? Well, we can use robot simulators basically and specify as input some virtual environment, perhaps have a way to generate it with some domain randomization, or have some way of generating arbitrary, reasonably looking floor layouts. I think AWS has done that with their WorldForge software, and there's some other applications like that. So you basically generate a virtual environment for your robot that satisfies certain constraints in terms of you don't want to have a chair flying around. You want to have its legs on the floor, and so on, so that it satisfies your expectation of a proper environment. And then you run your robot with all of its software in that virtual environment. And and the good thing about simulation is that the ground truth. You can just write some code to observe how the robot behavior evolves over time, and for example keep track of whether the footprint of the robot has covered everything that is your floor space. And you do not say it needs to exactly follow this path, because that test would break immediately with the next software version. You just say this condition needs to be satisfied with respect to the overall outcome. And I think that is something you usually do not see in a similar manner in other types of software. Um, that you need a full blown simulator in order to generate valid input data and to know whether what your software under test is doing is actually a valid output. And I think this is the main difference. And another one is the temporal nature of most robot behaviors. You're not just interested in one frame. You put one laser scan into your algorithm and you get one motor command out of it again, but you actually want to track that over time, because whatever action the robot takes at time step t will influence what it perceives then in the next time step t plus 1. And this temporal coupling, or the sequential nature of it, is also something you do not have, I think, to the same extent or at the same level of complexity in any non-robot software.
Do you think so? I mean, I'm thinking about testing frameworks for web applications, and they do struggle with these problems, although maybe not to the same extent. And so they'll have frameworks that kind of like will open, or it'll have like a Chromium based browser, and you can simulate things like like a 3G or 2G network connection kind of thing, and like waiting for things to load. And then you say, go click this field, fill in the data, make sure something auto completes, this kind of thing. So that seems somewhat similar to this, although, and I guess in those cases, what you're also doing is you're writing a very specific function that says, I should see this later. In the case where you're going around on the floor and you want to make sure it's all covered, you probably want to do a way to make sure that the robot's vacuum covered every part of the floor during the path it took, or with the path that it proposes. And in the web one, maybe you just check that whatever rendered correctly, or you're in the state you expect, or whatever it is, but you need some function to validate that. And that seems to take a lot of expertise to me. And that seems hard because also you need to, like a lot of times if you're incentivized to push and make and do the software as quick as possible, it's hard to go, okay, I'm going to really do this unit test correctly, or not this integration test correctly, by going, this is where the vacuum is. Okay, now I have the full path of the robot, and I'm going to see that that path indeed does cover the whole thing. And then I want to see that the robot didn't deviate from the path too much in actually trying to execute it, or something like this. And maybe that can be the passing set of tests for this. But like that's hard to do for this.
Yeah, I guess in general, one of the hardest parts about doing good testing for robotics is not figuring out how to do it in theory, but actually being able to do it in practice. And the biggest obstacle are most likely not technical ones, but as you mentioned, there is the iron project triangle. You have so much resources, so much time, and are expected to deliver that much scope. So then the other dimension is quality, and quality in software is mostly determined by process and testing. Not let's not perhaps talk about formal verification. I know there's research going on and so on, but robotics might be one of the later fields that finds application of formal verification in practice due to the multi-dimensional continuous state space of it.
Once we
um,
understand neural networks, we'll get to that probably as
yeah,
a community.
exactly. Then after that, we go to applying it to robotics. So doing it in practice is definitely one of the big challenges. And another part that I didn't mention yet, where robot software is difficult, is, well, it is intended to run on a real robot. So I talked about testing the software in simulation, kind of software in the loop testing, but at some point in time you also really want to make sure that it does not only run correctly in simulation but also on the real robot. So you need some kind of hardware in the loop testing, also, where you have either a test bench with some components on it, partial robot, or a robot without an end effector going through its motions, or you have a mobile robot in 2-3 rooms somewhere, and it's being testing the latest release or beta release there, or you have full blown testing warehouse where you just run your latest software release. So this aspect of that, at some point you need to test it on the real hardware before you ship it out to customers, is an additional complexity. So what I would recommend is, given that we all have limited time for quality assurance in the end of the day, and um, yeah, we all want to create better software, more reliable software, but yeah, sometimes we need to make amends for the reality of limited resources and limited budgets. My recommendation would actually be to focus on the two ends of the spectrum then. So do good and proper unit testing, but then skip some of the intermediate steps I mentioned earlier and do good software in the loop, meaning simulation testing, and build up some hardware in the loop testing, so that you really have the confidence that your next software update will not break hundreds or even thousands of robots in the field, because most likely if that happens, your company is no more. Fixing that, going to thousands of robot installations, is so expensive. Yeah, that will likely destroy the entire company. So there's an interesting paper by some of my colleagues from Norway, from ABB Robotics. They describe how they are testing their paint robot system, and they have published a very detailed paper about integrating hardware in the loop testing, making the best use of a limited number of hardware setups in terms of which test cases you run, optimizing for the coverage by the least amount of test cases on hardware. So that's, I think, a really interesting approach to make hardware in the loop. We need it. I think everyone needs a couple hardware in the loop test systems in-house before they ship software to customers. But making good use of them should be high on your priority list, and this consideration of test scheduling or intelligent test scheduling, I think, is a valuable one here.
Yeah, I think so too. How does it work at a heuristic level? Does the person create a big configuration file, and that configuration file says we have this and this and this and this and this, and this is the relative importance, and this is its similarity to this other thing? Or how does it work to, because I imagine it's basically trying to develop, it's like doing a principal component analysis or something on the test space. And so it's trying to see with the fewest things what can cover the most, is what I would imagine. But I mean, how do you take something that's abstract like your testing suite and turn it into something like that?
So I don't know the specific algorithm they use by heart from the top of my head. I know they use some constraint programming and basically doing a heuristic version of set coverage. But it brings me to a very interesting point you bring up there, and that is, testing starts with knowing your requirements. It starts with actually having a specification or some requirements how the system should behave, and their input is basically these requirements, and then they try to figure out, if something has changed, which tests best cover the newly changed parts and validate that the requirements are still satisfied.
So
um,
there's some dependency management here where you go,
Basically,
this changed, and then it has a graph of everything and how it relates to everything else. And it says, okay, so we touched all those things,
yeah,
this kind of thing. So you figure out the minimal set, and then maybe from there you prioritize with the available time or
yeah,
something. Sounds like a lot
exactly.
of configuration, but
Yeah, I think they wrote a nice software piece of software for it that tries to so you need to keep the specification up to date, your input, but then the software basically automatically comes up with an optimal test plan or close to optimal test plan, so that you and then that one just gets deployed down to the real hardware and execute, and you get your test results back, so that there's really little manual things you need to do day in day out, because otherwise, yeah, whatever isn't properly automated and becomes a pain or a bottleneck will soon not be done anymore. So I think so perhaps that's another important point, apart from knowing what you should actually be testing, by knowing what your system is actually supposed to do. It sounds trivial, but I have often seen this not being that clear. But another point is really you need to automate all manual tests. At some point you will not run anymore. You cannot sustain it. You cannot keep arguing for the headcount for it, and then it will just you will have your tests, but you will not run them anymore. So automation is key. And interestingly, I think, as I said before, autonomous vehicles for me is part of robotics. And they have really been one of the pioneers now in the last decade to say, we cannot just have hundreds of cars running around on public streets or build, large artificial towns in the desert where we can test our software. So we need to do it in simulation. And I think they have had a lot of success actually by building a substantial amount of these software in the loop test cases for their AV software. And that hasn't yet reached industrial and service robotics, I think, to the same extent. But of course, they have also big budgets and big teams behind it, because yes, it is a lot of effort. But the alternative is not doing it and having a lot of field failures. And there's nothing worse than having, first of all, to explain to the customer why their production has just stopped, and sending your service technicians into the field to fix things. And I once taught middle school children, robotics and software engineering. I told them, be careful, if your software crashes, you need to restart it. But if your robot crashes, you might have to reassemble it. So that's of course another point. With a failure in robotics is potentially much more expensive to mediate than it is in other. Well, of course, if you are a big web company and some bug deletes your database, you also have a big problem. Uh, but yeah, in robotics, the difference between being 5 millimeters above the table and 5 millimeters below the table is not a continuous difference.
oh man, let's see. So we are running out of time. Um, I'm wondering, do you have any resources that you recommend people to learn more about testing and like maybe heuristics for how to design robotics systems with adequate testing?
So, of course, apart from a future chapter in my own book that I'm currently writing, there will be a chapter on software engineering for robotics. Um, apart from that, of course, there's also existing literature, and perhaps I can send you a few pointers to put into the show notes on papers. There's, I think, some recorded conference talks that are interesting. But I think the biggest or the simplest summary is, if you're practicing DevOps and if you have understood why it is so important to have a continuous integration and potentially a continuous deployment pipeline, don't use having hardware or don't use having robots as an excuse to go away from it. You need to extend your DevOps to, let's call it RobOps or some other term. You really need to, if you want to keep efficiency high, also you're working in robotics and you want to keep quality high, you just need to continue automating things like you have done it before. The days of people manually deploying software to servers and manually migrating databases are over, at least at large. And we need to also get to a point in robotics where nobody downloads the latest software manually to the robot and then runs the robot around the lab with a joystick by hand. But we need to automate it to the same level. Only then we can achieve the same productivity and reliability, and also the same developer happiness as in other parts where we do not have those additional challenges coming from robotics.
Mm-hmm. Let's see. Any advice for someone who is, say, early in their career in robotics?
So I would recommend, of course, to stay on that path, even though it's sometimes a hard and difficult path to get proficient in robotics. There's so much software, physics, math, and a whole lot of other things around it. But it's very rewarding. So that's perhaps one topic. The other one is to figure out to get the broad overview of the field, and then find your initial point of focus. So it's good if you can talk to the colleagues that build the web front end. It's good to be able to understand what the people in the control engineering are doing. Learn their language, get an overview of it, but at the same time realize that the lone genius that you see in some Hollywood movies that builds the next generation humanoids on their own in some lab in some jungle, that's not realistic. Robotics is a complex, diverse field. It pulls in all of mechatronics, cyber physical systems, embedded, and so on and so forth. So division of labor is key. So get an overview, but then find your focus point. That I can definitely recommend.
Awesome. And do you have any links or contact info or anything you'd like to share with our watchers and listeners?
So it's best to. I'm most active on LinkedIn. So that's if you want to hear what I'm sharing and posting and the latest when new chapters of my book are released and become available to read. Connect to me on LinkedIn. If you search for my name, you will find me easily. I think that's the best way to reach out. Actually, I'm also on Twitter, but not as active.
Gotcha. All right. Thank you. It was nice speaking with you.
Yeah, it was a pleasure, and looking forward to the next episodes coming out and listening to them again.
All right. Hell yeah. Thank you. Bye, everyone.
Goodbye.